Mr. Lasuna, Houston, what do you think the universe is expanding into? Is it getting faster or slower? And is it right to say that the observable universe doesn't relate specifically to an edge? It's expanding into a void. That's the best way that we can say. It's just there's nothingness out there, and some universe is spilling into it. It is getting faster. That's what Alexei Filipenko and his team discovered when they discovered dark energy. Is that the universe initially exploded, boom, into existence. There was a big inflation at first, and then everything started gradually slowing down until about 6 billion years ago, when suddenly everything started speeding up again. And that is dark energy now being more powerful than the force of gravity trying to pull everything back together. And my undergraduate thesis was on the what could be the cause of that dark energy. And I settled on the random appearance and disappearance of matter and antimatter that happens everywhere, all the time, all around us. And when matter and antimatter blink into existence, they collide, disappear again, but leave behind a gamma ray photon. And those photons go out in all sorts of different directions. And eventually they create these planar waves, sort of like solar sails, that at great enough distances now account for more outward pressure than inward pressure of gravitational pull between large galaxy clusters. So the universe is speeding up because there's more power pushing out than there is power pulling in. And yes, the observable universe does not relate specifically to an edge. What we see at the observable universe is one of two things. One, the fuzz of the Big Bang. So the microwave background radiation, or background microwave radiation, whatever I want to say it. And that is just the noise from when matter first started to appear after the Big Bang. And if you look far enough back in time, in any direction, you see that fuzz. And it's just this static. Like you turn on old school TV and goes, you get the salt and pepper snow. You're looking at the Big Bang, essentially. So that is sort of this veil that we can't pierce. And it also happens to be around the point of the beginning of the universe when we didn't really have stars or galaxies or anything else. So the first little red things we see forming are these proto-galaxies, these energetic quasars where the galaxies are forming and stars are being born, and there's a lot of energy coming out of them. But because the universe is expanding and those things are receding away from us, the Doppler effect takes what would have been a really intense light that would have been an X-ray and ultraviolet and everything, and has redshifted it into this like really faded, kind of color of my shirt, little dots out in the distance. And at some point, we will get to where the universe is old enough and everything's expanding away so fast that it just disappears from view, and we just can't see it anymore. We might not even see the cosmic microwave background radiation at some point because it may fade away into nothing as it expands away from us. So that's kind of everything just kind of gets hazy out there and disappears. What we have is what was called a light cone. So if time 0, when the universe began, is at the bottom, there's this cone that comes up, and we are at the top of the cone. Anything outside of that is expanding way faster than the speed of light. So we can only see this one little conical section of the sphere that is the universe. And we've tried to calculate how big that sphere is. There's a lot of error involved, but we might only be able to see about 15% of the visible universe. The rest of it is other conical sections that we cannot see. So that's best guess we got. One of the reasons why I went into astronomy was there's so much error built into every calculation. As long as you're within order of magnitude or something, you're fine. Way easier to do the math. Okay. Scott Pullen. I can't read. Houston. I was reading about the satellite time issues that Artemis missions pose to other astronomical research projects, mainly satellite time for data transfer. Have you heard about this? Well, there's a couple of things. Artemis is the far side of the moon at points, which makes it I think, several seconds delay. So there's problems with delay and transfer and trying to relay information, especially if it's on the dark side. It disappears because it's not in line of sight of anything on the Earth. So I think what they want to do is they want to put sort of moon synchronous satellites that are visible to the dark side of the moon as well as the Earth's surface, so that we can relay information anytime we need. And because the Earth rotates, right, you need to have satellite stations all over the world so that at any time, whatever side happens to be facing the moon at that time can receive information. So NASA has setups in like Australia and Europe and things, so that they can get data transfers when North America itself cannot see what's going on with the moon. And all those systems are used for other projects, stuff that's on Mars, stuff that's probes that are going on the deep space, things like that. So, yeah. The article said that the 3 radio telescopes we used for talking with Hubble and JWST were paused so Artemis could have 24-hour comms during mission. If we pick up the launch cadence to the moon, will NASA build more radio telescopes on Earth, or do you think they will launch some radio telescopes to low Earth orbit? Your thoughts? I mean, we can use sort of radio dishes in low Earth orbit as we would communication satellites, but because radio waves don't get blocked by our atmosphere and they reach the Earth's surface just fine, it's much cheaper to build large radio dishes on the Earth's surface than it is to try and launch them into space. The whole reason we put JWST up there, James Webb Space Telescope, is because we don't see infrared very well. The carbon dioxide in our atmosphere blocks a lot of infrared light. You have to have these things at really high altitude to even get a little bit of infrared light from outer space. So you want to have a space telescope that looks in infrared, space telescopes that look in ultraviolet, space telescopes that look in gamma or X-rays, because our atmosphere blocks most of that. And thank God, because we'd be toast if it let in all the gamma rays. So like the Chandrasekhar telescope does X-rays and does some really beautiful pictures in X-ray up in space of objects. Probably the prettiest calendar I've seen is the Chandrasekhar calendar that Harvard pumps out each year.